All right, hello everyone. I'm feeling slightly annoyed because I just recorded this whole video, except I didn't actually press record. So here we go again. This one's going to be really good because I've had a lot of practice. So we are going to talk about the worksheet about hyperfine splitting. And so the point of this is that we talked about how the ground state of hydrogen 100, it's actually a four-dimensional space of states because you have the electrons with spin half and the proton with spin half. And so you actually have this basis of four different states where the electron spin and the proton spin are up, 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 down, down, up, and down, down. And on top of that, there's a physical interaction between the electron spin and the proton spin because both of them act like little magnets. And so what we said is that in this ground state level, when you want to take into account that extra effect and you calculate the matrix elements for that hyperfine Hamiltonian in our basis of four ground states, so that would be this 4x4 matrix, that turns out to be equivalent to having this system of two spin half particles and adding a perturbation h1, which is equal to some constant times the electron spin operator times the proton spin operator. Okay, and so we want to understand in this question, if I start with those states and I add that operator, what are going to be the energy shifts and what are going to be the various states corresponding to these energy shifts? Okay, so let's get started. So what we're going to do is use exactly the same trick as we used for the spin-orbit coupling. Okay, so let me remind you of that trick. So basically our states here at the top, those are eigenstates of Sz electron and Sz proton. Okay. In order to easily compute the matrix elements of this Hamiltonian, what we can do is realize that there's a nice way of rewriting that Hamiltonian in terms of the total spin operator. So what we can say is that this H1, we can alternatively write it as C over 2 times S total squared minus S electron squared minus S proton squared. Okay. And so what we want to do is work in the S total squared S total Z basis. Okay. And so we'll call those states Jm, where J indicates, so h bar squared times J plus 1 is going to be the eigenvalue for S total squared, and h bar times M is going to be the eigenvalue for S total Z. Okay, and now here we're talking about S total as just being the spin operator for the electron plus the spin operator for the proton, or the vector of operators. Our total angular momentum is 0 for this set of states, and so we're basically just we're just not considering that. We don't need to consider it because Lz is 0, Lx is 0, Ly is 0, L squared is 0. Okay, great. So what we want to do is first we can understand what are these new basis elements in terms of the old basis elements. That we can get using the Klebsch-Gordon table. And then we want to understand what is the energy shift once I add this Hamiltonian. Okay, and that's going to be very straightforward working in this new basis. Okay, so first let me just remind you then what are these basis elements? And so we're talking about a system where the electron has spin half and the proton has spin half. And then according to our general discussion last week, what we can have is either a total angular momentum of 0 or a total angular momentum of 1. Okay, so that's just following our general rule that the most you can have is the sum of the two, and the least you can have is the absolute value of the difference of the two spins. Okay, and we can write these states with a definite S total squared and a definite S total Z explicitly in terms of our original basis. Okay, and so we can just look it up on the Klebsch-Gordon table. So we're going to be looking at the 1/2 times 1/2 table. And so the spin 0 state, so there's just this one special spin 0 state, according to the table, that is going to be 1/√2 up and then down minus down up. Okay, and so I'm using this up-down notation. Let me just clarify that. So what I mean by that in detail would be Sz electron equals h bar over 2, Sz proton equals minus h bar over 2. Okay, so it's just a lot easier to write up, down than all of that. Okay, so that is your spin 0 state. The jargon for that, people often call that the singlet state of the two-spin system. And then the other states, they have spin 1. So our other basis elements are going to be the 1,1 state, a 1,0 state, and a 1-1 state. The jargon for these guys is the triplet. And we can write those again in terms of our original basis. So the 1,1 state is just up, up. Okay, so that will give you obviously a Z component of h bar, and a total spin turns out also to be h bar. The 1,0 is more interesting. It's like the singlet state, except you have a plus sign. And so you can check that because you have the plus sign, that state is going to be orthogonal to the other state. And then 1-1, that's the state down, down. Okay, and so those three states here, they all will mix together under rotations, but they won't mix with the singlet state. So now let's understand what are the energy shifts for these various states. Okay, and so we want to compute the matrix elements. In principle, we want to compute these matrix elements between our 4 basis states and the new basis, with H1 in the middle, and then Jm. But we're going to see that we're only going to get diagonal matrix elements here. Okay, so what we can notice is that H1 acting on Jm, let's move this up here. So that's equal to C over 2. Okay, now we act with S total squared, so that gives h bar squared j plus 1. And then minus S electron squared, that's just 3/4 h bar squared, because all of our states have spin half for the electron. And then minus S proton squared acting our state, and that's another 3/4 h bar squared. So I'll just write that all out. And then Jm again, because it's an eigenstate. Okay, and so now you see that if I now take the bra onto that, the inner product of that with some other state j prime m prime, it's going to vanish unless j prime equals j and m prime equals m, because those basis elements are chosen to be orthonormal to each other. Okay, and so so basically then we just get that for the j equals 1 states, then the energy shift is just going to be, you know, this diagonal matrix element of Jm with this guy. And so all we have to do is to find the energy shift for j equals 1 is to plug in j equals 1 into our formula here. And so that gives me c over 2 times 2h bar squared minus 3 halves h bar squared. So that is c over 4 h bar squared. Okay, and then for j equals 0, we plug in j equals 0 to our formula, and so that's minus, that turns out to be delta E j equals 0 equals minus 3c over 4 h bar squared. And so what you see, if I want to now draw a picture of our spectrum, before considering this perturbation, we just had 4 states and they all had the same energy. And now what you see is that the spin 0 state, up, down, minus, down, up, that ends up having a lower energy. Okay, so that is the true ground state of hydrogen, the 1, 0, 0 state for the orbital part, and then this net spin of 0, up, down, minus, down, up. And then at a slightly higher energy, you have this triplet of states with spin 1. Okay. Now in the next video, I'm going to talk about how big is that energy splitting in the actual hydrogen atom. It's going to be tiny, and I'm going to talk about why this is a really important, why the splitting is really important physically, particularly in our understanding and our ability to map the universe, to map hydrogen in the universe. So stay tuned for that.